system design. So I'm going to be going over basically all like the system design knowledge that I've studied. I've taken like a lot of notes on all this stuff and can probably like, make some content that's going to be useful. So we're just going to be recording. I've got a lot of content ideas, but we'll go into this one. Just go over my notes. And this time I think it'd be better too to have it as a video format as opposed to the other stuff because people just don't like reading notes a lot of the times. And so if you can have a video, it's, pretty solid. So let's go over to here. I think, let's see here. I'm trying to figure out how I even want to structure this. Monday, June, or what, June 17th. 2024. Cool. So, what's this? And I had a couple. All right, so let me, I think just close this, right? Cool. So, oh, nice. And my screen's not recording. Here we go. Perfect. So one, I want to talk about like HLD versus LLD. And also another thing too is that's relevant. Oh no, not this. Not this. Here. This here. So another thing, so I think I realized why my speed's lagging is because I'm at 20 FPS or whatever. Okay. Close this, restream. Yeah, so first things first is, right, like my, wait, where's my OBS thing? Okay. So my system design knowledge is coming from SDFC's kind of roadmap, right? So he made this roadmap and it was like basically like go over Don Martin's, go over Alex Hsu's, go over like some of DDIA. If you're trying to get into Fang, right? This is like Fang upper, higher end hiring bar, and then this one's like lower end, right? It's just like basic stuff. And we've got, LLD, cap theorem, all this stuff. Like what are all these things? And then here we got HLD fluency with trade-offs. Problems tend to be eventual consistency, high availability, load balancers, replication, partitioning. Like this is like pretty standard stuff for like a mid-level thing, I think. Like no one's really gonna ask you this stuff at all, in my opinion. Clock drift, like imagine being asked clock drift in a mid-level interview for system design. So well, yeah, what are all these things? Like, where can you start? I think there's a couple of things I want to go over. So, like, one, like, where to start, and then, let's see here. What are other things too? I mean, I guess I could really talk about all of these. I could go through Don Martin's. Intro. I could also go about just Alex Hsu, like V1, and go through every single like type thing, like web crawler, like web URL or whatever, or like tiny URL, and etc. And then do go through all of those for V2, and then go through stuff for DDIA. Think other stuff. What high level design, low level design? Where do you start? Like what roadmap to follow? What other things do we have? And then also I got this cool area. We got the sneak here. Oh. What else is there? What else is there? Don Martin's intro. So like this is gonna be all this stuff here, I feel like. So like low level design, because he mentions this stuff, but he's not actually talked about cap theorem. So then replication, partitioning. What else do we have? Partitions, horizontal scaling, NoSQL. And denormalization. Which he obviously covers for all. Yeah, the thing covers all of it, Don Martins. And then HLD stuff, load balancers. He kept cap theorem on here twice. Hand partitioning. That's kind of bad. Leader follower, eventual consistency, hot partitions. Then hot partitions, leader, follower, eventual consistency. So what I might do is just go through all these concepts. That's what I might do. And I think that's fine. Because like this is basically all of my system design knowledge. It's just like the Don Martin system design primer. Don E. Martin. I'm always kind of surprised, but also curious. Wait, what's this guy up to? He made this primer and then... Also, does he just have something that's just committing every day? What? Is he just committing every single day? It's kind of weird, right? Awesome AWS. There's no way he's actually been just coding every single day. No shot would I believe that. He has to have like some script that's doing this. That's doing it for him. For sure, right? I mean, I guess nothing in 2024, so no. I'm just curious, what's he up to? Coding challenges. And then I'm always like scared because I feel like LinkedIn will just pop stupid stuff up for like no reason. Okay. Don E. Martin. Meta software engineer. A lot of experience. Oh, he's an open source contributor. Okay. Cool. So I think we'll just get into it. All right. So let's go over the system design. Let's go over like, I guess, one big part of system design, studying for interviews. Do you think that this guy makes 6 figures? I mean, if he's at Meta for sure, right? Like, I don't know what but it doesn't really say what like part of it is he is, but Meta pays. If you ever want to know what companies pay, you just go to levels.fi. Let's go to levels.fi and then, you know, type in the company, right? Facebook, Meta, whatever. That's software engineer. Now, this guy has a lot more experience, but yeah, I mean, he's probably making like 500K a year at Meta. My guess is he's senior level. I don't think he would be mid-level with 20 years of experience, but you never know. That said, yeah, I mean, he makes a lot for sure. It's like a lot of software engineers in the US. All right, so yeah, so like, how do you, okay, why are we doing, I don't have really any notes on this, so this is probably gonna be kind of rough, but like, why do system design? Why is this even something like to even bother doing? Well, one is that companies will start asking it for the mid-level position. So once you have about 3 years of experience, you're gonna unlock a new door. Yeah, once you have about 3 years of experience, 3 or 4 years of experience, you're gonna unlock a new door of interview preparation, which is something else to study, which is system design. They're gonna ask you questions on this topic to design like systems and all of that, microservices, services, whatever, monoliths. And if you can't do it, then you're not going to get the job. This is particularly relevant for Fang, but it's actually asked for, I think, for most companies, because this is seen as like the more practical one as opposed to like doing like lead code stuff. So for that reason, I've read Designing Data Intensive Applications, Alex Hughes, Volume 1, Volume 2, Don Martin's System Design Primer, and then I also have a book, Hacking the System Design Interview. And those are really the 4 resources that I've read for this stuff. I've also done mock interviews, so I think I understand like what's needed. And if you go over here to my website, you can also see my notes if you're very curious to see like, what does this stuff entail on a summarized version. But what I'm going to do is I'm going to summarize this summary right now. We're going to go into how do you prepare? So how do you prepare for system design? And actually, what is system design? System design is typically like a high level overview of some kind of like application. So if we actually go here, nice. What is this? Alex, she has a Discord channel. The heck? NeetCode has one too. I should probably join NeetCode's Discord, honestly. But we're getting distracted now. But I should join his Discord, see what like people are talking about. I don't know how NeetCode feels about me though. I imagine he just doesn't care or know I exist. So I guess you could always make multiple accounts. So where's the System Design Fight Club guy? System Design Fight Club. I don't know why he names it this. I feel like there's like a lot of like kind of edgy like software engineers. It's like kind of weird. But okay, yeah, so like what is system design? So like you're going to be asked questions like design Twitter, design Reddit, Pastebin, whatever. And then you're going to be expected to draw like these diagrams that talk about like the state, and you're also going to be asked to like explain this stuff. What's up? Wait, what's up? NeetCode and you have beef because you're both huge players in the space. No, I mean, we don't have any beef. I haven't really said anything to him. I haven't really said anything to him. But it's not really because we're in the same space. I mean, it'd just be like if I guess criticize him, he might negatively have negative perceptions of me. So for example, if I say something bad about him and then he sees that, right, like he's just gonna be like, oh, I don't like this person. Not that I really say a whole lot of mean stuff about him, but I mean, I also don't like, I don't think he's like doing something perfect, like, right? So I'm gonna have criticisms over his stuff, especially over mine. Like one thing, for example, is NeetCode doesn't do any contests. For whatever reason, he started doing LeetCode contests and he got into Google and then he stopped doing them, but like he never recommends doing contests. I don't really understand why. I think that's like a very good thing to do, but like probably objectively, but that's like something I would disagree with, for example. But I mean, I don't have anything else. I've kind of said a lot of good things about him too. He kind of, helped change the space for DSA stuff. Like he helped make it a lot better. Bjergsen HS, what is up, man? Okay, going back to this. So yeah, for a system design interview, you're gonna be asked to like design like some kind of high level thing typically for the mid-level role. And they'll say like, oh, design Pastebin, and you gotta like, build out, oh, we've got like some upload service, right? We generate keys. It's overall system design is like it's a lot more flexible in the sense that like you're gonna be asked to build an application system in like 30 minutes or maybe an hour if you're lucky, but you're gonna be something that engineers spend 100 hours like trying to build. You're gonna be asked to do it in 30 minutes. So a lot of it is a lot of hand waving, a lot of things that don't really exist, and it's a lot of trying to figure out what does the interviewer want to focus on, because there's just way too many topics to talk about for like how to design YouTube. And they spend engineers, I mean, they have engineers spending 10 years or 5 years or whatever just trying to figure this thing out. But that's kind of like, I guess the bad news is that it's kind of amorphous, which is why this one's probably relies more, I think, on doing mock interviews to get good, and then also just having theoretical knowledge. So what's the roadmap and how do you start doing it? So if we go over to here, I actually really like this System Design Fight Club. I think his stuff's amazing. And what we can do is really for theory for a mid-level interview, what you want to do is go over to the Don Martin System Design Primer, right? And you can just like literally just search it, just Don Martin System Design Primer, Google it. You're going to read through all of this and you're going to know this stuff. I'm going to try to generally make an overview of this. for each of these things. And, you know, these concepts are going to be things like replication, partitions, things like that to make a scalable system. It's actually really easy to make a mid system or like a non-scalable system. It's just like, oh, you have like a server and then you have like a database. That's like the, you know, like level 1 of system design is that you have one user, and so the user just asks for something, and then the server asks for it in the database, and then it like gets sent up like this. So this is probably like the easiest like interview that you could have, but most of them aren't. Especially if you're interviewing at something like Facebook or Google, they're gonna ask you, oh, well, we want this to have multiple servers, and so you know it's like layered. Essentially, you have multiple servers, and because you have multiple servers, right, you're gonna have probably multiple databases depending on your server load and things like that. But anyways, another thing too that's worth mentioning is the yeah. So another thing that's worth mentioning is that there is low level design versus high level design for like a system design interview. And what does that means is that like there it's kind of like, again, more amorphous like type stuff. Like, you know, this is like really big things. And people use terms like in several different ways, so you actually have to ask for definitions. But low level design here is something that you have to know for mid level, which is like if you have an Amazon interview, they're going to ask you like design parking lot or something, and they want to actually see you write code to how like that parking lot would work. And I don't know why. Is this legitimate parking lot stuff? That's so stupid. So you're gonna be asked like stuff like this, where you have to write out actual code, like a class, object-oriented programming. So essentially you've got like two things. One, where you're trying to understand like scalability, and then two, you're trying to also understand like what does the code look like for these things? What design patterns can I use? What is like the solid principle, and how can I apply that? And they're gonna be testing you on your knowledge based off of that. So this is for the mid-level stuff. And again, if you can't not do this, if you don't know it, then you're just not going to pass the interview, and they're going to skip you over. It doesn't really matter, like, you know, the things that you've done, who you know, like, you know, nepotism, any of that stuff. It doesn't matter. It's just like, are you going to be able to draw this stuff out and code it out? Cool. So that's the why. That is why we're going over this stuff, is so you can improve at interviews, or if you want to, like, you know, kind of skip ahead, you don't really want to read these books. Okay, so resources, we'll go through these too because I actually like them. So Fireship does not do any system design stuff. I don't think that would be helpful at all, honestly, for system design. This guy doesn't do it either. And Byte is actually just very good. That's very good stuff. This for system design. So you can do is hop over to YouTube and go to Byte. I think he also has a course too, honestly, which I haven't bought it, but it might not be bad. But you can go to his YouTube channel, and he'll explain all these concepts, but he has a lot more diagrams. But I'm hoping to go more in depth than what he's going into. But if you want like a very, very brief overview, like 10-minute video, like again, this video is going to be 2 hours long, right? Not 10 minutes. But if you want like bite-sized stuff that won't really get you there, but it'll make you like, I guess, not terrible, right? Go over there to the YouTube channel. I think that's probably the best one. I think NeetCode has also done some system design stuff, but again, it's good. It's like solid, right? It has this principle, right? We're talking about multiple servers, a DB, and then you have like a cache or something like here. And, you know, like CDNs or whatever, like all that kind of stuff, is that you're just mapping this. And it's, you know, a good introduction to that. Exponent interview IO, like these are like solid, I guess. Like it's not amazing at all by any means. This channel is really good though. Super high in depth. System Design Fight Club. So yeah, this is like the roadmap I would recommend if you're trying to do this stuff. If you're actually trying to like go, you know, super in depth. This is the route I've gone. I've tried, you know, I've looked at NeetCode's videos. I've looked at Byte. I've looked at System Design Interview, Hacking the System Design Interview, Alex Shu V2, DDIA, and then Don Martin. So a lot of resources. I'm gonna try to distill those down into something within like the next 2 hours. So let's get into it. So this is what we're covering. HLD versus LLD. So I'm not going to be going over the LLD stuff. If you want to do object-oriented programming, I guess just go to a YouTube channel or just practice it on your own. building things. So I don't know what I actually want to do first, because I also don't remember like a whole lot. Yeah, I have like no idea. Let's summarize, I guess, all of DDIA because it's probably the freshest on my mind and will probably be good. So yeah, let's start with that. Okay, so yeah, I'm gonna film this intro real quick. Okay, I've read 5 different system design books, Designing Data Intensive Applications, Alex Hughes, Volume 1, Volume 2, Don Martin System Design Primer. I've done mock interviews also, and in today's video, we're going to be going over designing data intensive applications and what does all that stuff mean. So let's look at this. So I'm just going to go through these chapters, I think, and maybe like draw on diagrams to explain them. I think that's probably going to be cleanest, probably less effort for me. So, okay, chapters 1 through 3. So we got chapter 1, right? So this chapter starts off with Kleppman introducing like what is a system essentially, or like what that like data is like probably like the most important or the hardest like challenge that we have right now, and designing like something that's proper is going to be important, right? Like I mentioned like these buzzwords, so like AWS, NoSQL, it's really all about trade-offs and understanding like, you know, when to use what in what scenario. And so there's like 3 components of software. You want to make sure it's reliable, you want to make sure it's scalable, you want to make sure it's maintainable. What do these mean? I guess we'll go into these. Reliability, right? You want to make sure that the system does what it says and that like it's going to be consistent. If somebody asks for something, like you probably don't want it to give like random stuff. Just people aren't going to want to use an application like that, right? There's also like hardware errors and things like that, but you probably want to just prevent errors from happening ideally. And then show what the current load is. Latency versus response time. I don't know if this matters. Not sure if this really matters yet. Not yet. Maybe in the future. And then scalability is going to be like, are we going to be able to use this to millions of users? So if we have one person who uses the website, right? Like, yeah, sure, it works for this one person. Oh, wow, nice. So yeah, we have one person who uses it and it works for them, but like, why is this not? I'm so confused. Yeah, sure, this application works for one users, but like, what about everybody else? Like, is it gonna fail for them? We want to make sure that it's not. Do you prefer Google Drawing over Scala? This isn't even Google Drawing. I mean, I just like this because I can do it fast, and I don't feel like learning Scala Draw. Like the thing with like I like with this is that if I put down a box, I can immediately type into it. But with a Scala Draw, I have to put down the box, and then it like I put down the box, and then I can't type in it. Why? You don't think that like that would be like a nice feature? Is that when somebody puts a box down, just let them type into it? So then here I've got to say, oh, I want to type into it. Let's go 7 to type, I guess, and then not 7. What is it? 8, I guess. I don't even know, man. I don't know. Like the only difference I think I would do is there no other way to like? I feel like it's an important thing, right? Why would who draws a box and then they say like, oh, I actually have no intention of typing in this. Like I see you can double type, but then it does the thing where it's like separate. So then if you draw it, it's a separate entity. I don't know. Yeah. I like how ScalaDraw looks, and I like how like it's way smoother, but for this one I just like, oh, I can just drag. Okay, cool. Now we're typing. Most templates already have the label of the system, but that makes sense. I don't know. But okay, yeah, so what is scalability, right? Scalability is the idea that like if one person accesses something, like yeah, sure, it works for this one person. But like what about for the other like 50,000 people? Will it work for them? And so it's this idea of designing a system that can handle millions of users, tens of millions of users, billions of users, and things like that, right? Like TikTok, you know, is getting up to billions. And this is probably like the hardest part, honestly, of a system design interview, as I kind of mentioned before, is that, let me go back to actually, where am I thinking? Oh, here, right? Is that like reliability, like this is, you know, kind of the object oriented programming feels like the approach where you just want like to make sure that you want to write good tests. You want to make sure that like there's like systems in place that when somebody like actually does something, you can roll back. But scalability is like the hard thing because there's a lot of problems when it comes to when you need to build out several servers. For most startups, it's just like, hey, like do reliability and then do maintainability. Let's maintainability being like the idea that we can evolve our code over time and that it's not going to be like a massive hassle of like spaghetti code where you make a feature and then it breaks other things, right? We want it to where this is like long lasting ideally. And this is the kind of three tenets of this book, although I think it's mostly focused on scalability. Because this is just like it's just a much harder thing to actually do, right? There's a lot of books on how to write good tests and things like that, and a lot of LinkedIn gurus talking about all this stuff because this is like the low hanging fruit in my opinion. But okay, cool. So let's go into number 2, right? So how do we store data? This is going to be like the biggest thing, right? What database do we want to use? Do we want to use a database at all? And if you read in chapter 2, like this is what he's going over. Right. Okay. So we have like relational databases versus document-based SQL databases, right? How are you going to know? What are the pros and cons of them? How do you know which one to use? The TLDR is that you want to use relational when I feel like for ACID properties. So like when you have data that you really want to make sure is like correct. And then, and if you have like complex joins and things like that. And then for the document model, or like a NoSQL type of model is like helps with like scalability or like if you just don't have like those problems. And yeah, so we'll say like one to many, JSON is hard, a document model. These are just like more historical stuff, I think. Schema flexibility, right? Don't need to enforce stuff. Relational has a schemas, like the schemas really matter. You can't be flexible. Data locality, query languages. I've heard that like graph databases don't even like matter apparently. Like a graph database is just like a NoSQL database, but it just has like fancier like syntax that you can use. And let's see, property graph model. Like again, I don't think these are like super, like even super relevant. I don't really hear them talked about, and I also don't see them like really designed that much. Okay. So oh, also another thing that I want to talk about. Right. So like another interesting thing about system design is that it's way more like biology in that like you can actually just learn it by just watching lectures or like just reading books. Unlike like theory is like a lot nicer for system design than like data structure and algorithms, which is like math or physics where you have to practice solving problems in order to get better. But yeah, that's something I just want to bring up. So here we've got like, you know, chapter 3, which I guess is deeper into actually storing the data. So like, what are ways that we can actually store them? We talk about SQL and NoSQL, but like, what is that? What even is that? What is it underneath, like, you know, that hood of it? And so here we get into these like actual methods. So we've got like, oh, well, we can just store data as a file. So we, you know, literally pop open a TXT file, right? and then we just like start writing records like, oh, this happened, this happened, this happened. But then like what happens if we want like a backup? What happens if we want to like search for something individually? Well, now we've got to search the entire file, and that's like an O of N operation, obviously, right? And these are slow. So how can we do better? And we've got like write ahead logs, which is where we keep track of the offset, and then we just write based off of that. Right, so this is like version 2, where we write, but then we're like, oh, well, I want to go to this offset, and now we can actually immediately go there in like O of 1, right? And we can write and write. You have to practice drawing out the system, though. I don't know, wait, what do you mean by that, Big Blaster? I don't know, I don't understand what you mean by that. Yeah, like, I mean, yeah, mock interviews are huge. Like, you have to actually practice drawing out the system, but like what I'm saying, or I understand what you're saying. You're saying that when I was talking about studying, right, is that like you can actually just like watch videos for system design. Yeah, like, yeah, you have to practice out like drawing, and like mock interviews are going to be important. But if you don't practice lead code, you will fail like every single interview that you do. Like, you have to practice. Like, you can't watch videos of like somebody else doing it. You can't like it's like just way different. Like, you actually have to practice. And most people don't even understand that when it comes to like algorithms and stuff, is that like you need to practice and learn new things. For system design, you can actually just watch videos of people drawing out systems and then try mapping them out yourself, but like you're more or less going to get there. When an interviewer asks you like, oh, what is a cache, like that's just something you have to know. You have to just memorize it, or you know how any of this stuff works, right? Yeah, like, you know, like when I'm talking about these write ahead logs, like you kind of just have to know this stuff, and this is something that you don't really see a lot for DSA. Yeah, like if you just study your notes, you take notes on it, you study, you read the notes, like you'll be fine probably. But you should do mock interviews for sure. I mean, that's really gonna seal the deal in, because there's a lot of nuance in the interviews, where sometimes an interviewer wants you to talk about write ahead logs, the other times they don't want you to. You said you can learn systems with a book. Yeah, but I feel like you need to draw it. Yeah, like, yeah, it helps drawing for sure, and that, like, you know, will help you practice. But it's a lot more like biology, I think, where there's just like concepts you have to know. So anyways, we'll go into this, right? So we have this crash recovery, right? We can have like snapshots. So in case something, if this write log fails, we have like copies of it, and we keep track of like what's the last thing that we wrote to, like here, right? So that we know that if it fails, then we know that we can just copy up to everything that we did up to there. And then this is what SS tables and LSM trees. This is how NoSQL databases typically work. Not all NoSQL, right? Depends. NoSQL is pretty flexible, but this is how Cassandra works. It's a pretty famous thing, which is using SS table. What is an SS table? I also don't really know. I just know it's good for writes, honestly. That's it in these notes. It probably explains it. I don't know. And then we've got B trees, which are good for reads. And this is what MySQL uses, a B tree. And it's also what DynamoDB uses. But it's, you know, it depends, right? We get write heavy requests. We got good reads requests, B trees. Right, and then we get other data structures too for these. And then we also have analytic databases. So if you have to like run queries on things multiple times, right, that's another type of database that you're probably going to want. So, you know, somebody designed something that was like really good at storing for queries. So instead of like let's say you want to get all, you know, people in the United States, well, you would just like store that data into the table, into the row, so that you can just query that repeatedly. Or I guess it's what I think they're called column-based tables. So you can have over 100 columns. I guess it's somewhere in the book that I don't have written here, but essentially instead of querying rows, like, you know, like you would normally do, you can just store all of the queries like pre-computed and just store that data like as its own kind of row, so to speak. And then you don't have to check every single row like you normally, or every single column. You don't have to check every single column to see like, oh, who's from the United States and who has like this thing. That's probably like a really bad explanation, honestly. I need to actually study back up on that. But anyways, okay, this is like the first like chapters 1 through 3. So we did this in 15 minutes. Now we're gonna go into like more advanced stuff. Give me 1 second so I need to eat, and then we're gonna continue this. So I'll be right back. I should probably honestly stop the stream so my computer doesn't overheat, and then come back. I'll be back in 30 minutes. Is there a link to this doc? Yeah, so like I'm going over all of my DDIA notes. So here's like the link to that. And then I based all of this off of this guy's roadmap, the System Design Fight Club roadmap. So these are my system design notes that I'm going to be going over for the next 2 hours or an hour and 30 minutes for designing data intensive applications. And then for the GitHub repo of like the roadmap that I followed is this one. Cool. Yeah, I'll be right back. True, he is the GOAT. what is this? My man's traveling at 8.3 hours per minute. What does that mean? Traveling? Oh, well, I'm in the BR back one, bro. I was eating. I was eating, but now we're back. Now we're back. Now we're back. The glump. The biggin. The biggin, the biggin. It's like 10 minutes, I think. Anyways, all right, let's get back into this system design stuff. We're going to be going through DDIA and yeah, I believe that's it. So just to recap, really quickly over like the thing that I went over before is that through chapters 1 through 3, right? Chapters 1 like kind of sets up the tone of okay, what is system design and like why are we doing it? Which is that we want three things. We want reliability, scalability, maintainability. Right? Reliability is this idea that like when we have an application or like someone's using like our service or whatever, our app, that it's going to be reliable. It's not going to throw random errors. The hardware, if the hardware does break, we have like things in place that are going to prevent it from, destroying the system, shutting it down. We want to have like something that's like consistent where it's like not randomly breaking and things like that. Scalability is going to refer to the fact that we want systems that can handle like multiple users, right? So like, yeah, sure, our system works for one person, but what about for a million people, right? Is it going to work for is it going to work for more people essentially? And then maintainability is that, okay, we can make changes to this code base in the future. And like, there's not going to be like a ton of like spaghetti code or things like that, right? These are, yeah, pretty broadly, right? Like across all applications, this is like what we want. And if you actually look, maybe like what you learn in college, or if you look at what you learn in college, or if you look at what is taught in school, or what you see people probably posting on LinkedIn, they're probably just talking about this thing. You want to make it reliable, you want to make it maintainable. Like you'll hear this just ad nauseum, I feel like, especially on LinkedIn. But I also know maybe I'm probably on YouTube channels too. If you go to Primeagen, nobody really talks about the scalability thing because this is something that really only big companies care about. But this is also the hardest part, and this is where in my opinion, most of like the complexity of DDIA comes from, is scalability. How do we make this out for bigger people? But yeah, object-oriented programming, little design, it's like covering these two. Writing good tests and all that. So yeah, that's that. And then we go into the second part of the chapter, which is data models, right? So the big thing is, how do we store data, right? Should we use SQL? Should we use NoSQL? What are the trade-offs? What are the pros? What are the cons? How do we know like which one to use? What are they? And the TLDR on this one, right, is that you're probably going to want to use SQL if you have like a ton of complex joins or like many to many relationships. Then it's going to be really hard, like, and annoying to use like relational databases. But if you also have like really tight constraints, like you need like a really tight schema, you need like you want like ACID essentially, right, which is atomic, consistent, isolation, durable. If you want like that type of thing, then okay, relational is going to be good. But overall, right, like if it's like a banking application, you just don't want like things like fail randomly or stuff to happen, and someone loses like $1,000 or $1 million. Probably just stick with a relational and TLDR on that one. But there's also graph databases, which apparently like these aren't useful, but there's that. And then we have like an even deeper dive into the data. So like, what is SQL? What is SQL? And like, what do we do with that? Like, yeah, sure, okay, I know SQL is good for like banking applications or whatever, but like I know it's good for ACID, but like, what is it? And how does it like, what makes it good? And then what makes NoSQL good? And like, what are the ways that we can actually store things? And for chapter 3, this is going to go over this idea that, okay, well, we could just store everything in a TXT file, like just right there. That is my database. TXT is my database. So I just write everything here, and then when I want to search for something, I just say like, oh, let's just do like an O of N search through like the entire thing. Oh my god, I'm not even sharing, like my screen is not even sharing. Oh my god, kill me. I have to redo all this thing all over again. Oh boy. I'm new to your channel. Are you looking for a new job by doing leak code and study LSD, or is this just your hobby? It's kind of, I think probably both at this point. Wait, are you serious? Wait, was my mic muted this entire time? Oh my god. I just made so many mistakes. I don't understand how that happened. I'm new to the channel. Are you looking for a new job by studying leak code and study system design, or is it just your hobby? I think at this point it's just my hobby. Yeah, I think at this point it's just my hobby. I started doing leak code and system design just for like the job interview preparation stuff, but I think it might turn into something where I like try to like turn it into like a business, honestly. But at this, like, leak code for sure is I'm gonna be doing that as a hobby. I like it, it's fun. System design, I'm not sure. I need it to pass interviews, but it's, yeah, it might be sticking around. Yeah, my mic was muted. Your mic wasn't muted? Okay, cool. Nice. I don't know how it like got muted, but yeah. Anyways, a lot of mistakes here. But yeah, so anyways, that's where we're at right now. I like, like when I mentioned like as a hobby, right? Like I might just read this thing like high key just for fun. Database internals. Like why not? Like fuck it. Right? So I'm talking about database internals right now, actually. I'm about to, but we can go even deeper into what is a database. And then, maybe read these books too. Like the knowledge generally never stops. There's always stuff to learn. But this would not be for a job because I'm overkill right now. Any leak code problem I solve is overkill, and any system design thing I was overkill. But that's it. I think I might be able to like turn this into a business where I can maybe try to make videos that are just better than the other people that are out there, or just more helpful, right? Just things that are just more helpful. For some reason, nobody's ever like really gone chapter by chapter on DDIA. Don't know why. Nobody just really cares, I guess. Okay. Anyways, so I don't know. I mean, I guess I kind of have to like just redo this. I'm gonna redo this. Okay. So, right. So the first chapter of designing data intensive applications is going over reliability. Like, what is like a system? What is a good application? How do we know what that is, right? And he boils it down to three concepts, which is reliability, scalability, maintainability. Right? Reliability is this idea that if your program throws an error, it's gonna be like some kind of consistent error that like users are gonna know what is wrong, right? Like if somebody like tries to send money to their friend, that if it throws an error, right? Like one, it shouldn't really even throwing errors. But if it does throw an error, that they can at least know that, and that the system isn't just going to completely die because of that one case. Number two is scalability, right? So it's okay, sure, your program works for one person, but can it work for 1 million people at the same time, right? And then maintainability is the idea of like, can it evolve over time? Is it, if you make a change to it, is there like a ton of spaghetti code and you fix one thing and then it breaks everything else, right? So that's chapter one. And in my opinion, I think that, let's see, in my opinion, I think that like, this is like probably the core part of his book is the scalability, because this is like, again, we talk about a lot about reliability, which I misspelled, and maintainability, which I also misspelled. And the core thing is also I misspelled scalability. Bro, what happened here? Did I scale ability? Maybe I didn't actually. I don't know. Scale? I don't know. But yeah, the hard part is like doing this is like everybody already talks about this stuff, like, test driven development and all that. But nobody really talks about scalability. So well, most people also don't really need to know about it. So that's probably the reason. So then we go into when should you use SQL, NoSQL, and I guess just briefly going over this, it's going to be use SQL when you want like ACID or like really strict parameters. ACID being like that consistent things happen, that like there's no like dirty reads or dirty writes or things like that, where people are like reading data they're not supposed to be reading, or like race conditions and things like that. Like for example, for like a banking application where somebody like accidentally loses $1,000 just because the system was, or the database like had a hiccup. And then graph models. And okay, how do you actually store the data? So the third chapter is like, okay, we talk about like the pros and cons of NoSQL and SQL, but like what actually is that inside the data. And what you're gonna notice here is that like, okay, so the base thing is just like we just store it as a TXT file, right? Now the problem is that doesn't really scale. If we got a lot of data, we're doing like an O of N thing whenever we do want to look up some specific type of data, right? If we want to know what was said here, well, now we got to go through the entire thing, and that's like very expensive, and it's just not going to work on like large scale applications where we've got lots of text files. So the next level of that is that you can have a write ahead log, right? So we can say a wall, which is that we write the data every single time it gets appended to the end, but we also keep track of the offsets, so that now we can like, if we know like this one is located at like index 2 or something, we can actually just jump to index 2 directly and read it. So now it's like O of 1 if we know like what the offset is, or off like with that data. And this is nice. This is, you see this in like message queues and stuff, although I don't think he mentions it in his book at this point. And there's things like, okay, so what do you do if it needs to be recovered, right? What happens if like the server crashes and it was writing and like it broke? Well, you can have copies, right? You can take snapshots. You can keep track of every single thing that you've written in like a very long log. And then when you go there, you say, oh, well, let's just redo everything up to like our, our endpoint or whatever. Right. And then, right. So appending is fast, crash recovery simple, removing old segments, removes need. And then hash table must fit in memory, and then range queries are difficult, right? So range queries is like, what if we want to, so it's O of 1 for one entry, but like, what if we want multiple? And we have to kind of like jump the needle several times, I think, to actually retrieve that, which is expensive. Cool. So then we move into the SS tables and LSM trees. Now again, I don't remember this fully. I truly don't remember it, but I just know that these are slow at reading. I think because they have to write multiple copies of data or something, but I just know that they're slow when it comes to reads. And then B trees are good for reads. And this is what a SQL database uses, a B tree. So instead of having like this file like this, we can create some kind of tree structure, store files. Why am I doing arrows? Store files like this. And then we want to retrieve them. Now it's like login. Right? Look at that. Log in. What is LC and SD? LC is system design. LC is leak code. SD is system design. Yeah, that is what that is. Bjergsen. It says my like upload speed is like super low. I'm hitting like 3K bits per second. It's kind of weird. I don't know. I guess it's not affecting the stream though. Cool. So what other structures, right? So like there's other things. Actually, these are really the core. I'm sure there's like other ones like primary keys, and I guess there's stuff like here. And there's also column-based indices, which is another thing I wanted to talk about. Oh, and then there's also full text search thing. So Elasticsearch. So there's another idea too, where you can have like if you want to like search for text, like let's say we've got like Twitter and we've got like a ton of files or whatever. What you can do is you can use an inverted, I think it's called an inverted tree. I don't remember. But essentially the way it works is that you say like, oh, well, if I'm looking for cat is going to be in document 1, is going to be in document 2, and like document 3. And so that whenever we want to know like, oh, what are all like the documents that contain cat, we can just like, pull that up essentially from there. And you do that for like cat or like hat, maybe that's like doc 0 or something. but this is a faster way of like, if we want to like parse and search something. So like, the man, like the man or something. We want to search all tweets that say the man. Well, we can just kind of go through our tree, and then it'll like tell us like what things have like, you know, all these words. But this is Elasticsearch, which is again very popular, a very popular kind of service for like this full text searching thing. But again, I don't think he mentioned it in here, but just something. John, oh, you're online. Yep. Your stream is fine. Okay, cool. Nice. Thanks. Okay, second thing here too is we got, so analytics type of databases. And again, I think analytics is essentially the same. It's just like, so it says data warehouse is typically a relational database for queries. And then one central table that branches off into dimension tables. And I might be wrong here. Maybe this is something I should look up, but like, I think that when you have you have like a typical database or whatever, which is just like this, you've got like your rows, right? These are all going to be every single entry, and you got like your columns right here. And then typically if you want to do a query, like you'll check every single row, which is like, you know, kind of big, right? It's like, I mean, that's probably O of n for like every, you know, n being like all the rows that you have. But what you can do is just store those queries as their own column. So then you take all of these and you say like, oh, well, maybe like these are like US people or something. I think this is the idea. And then you just kind of like store them. I think these are called column-based databases, although I should probably spin that. Maybe spin that up. But essentially the idea is just you can speed up your analytics queries. So like if you want, oh, I want someone from USA. I want the person from India. I want the people from, you know, like Russia or something. Instead of constantly doing like this O of n thing, when you want to run this like, you know, a million times, you can just like pre-compute it essentially. And then just like store the result of whatever it is. And I believe that's how it works. It's my understanding of it. Okay, cool. So that is that. Chapters 1 through 3 of DDIA. Let's go into the next one. So the next one is going to be encoding and evolution. Cool. And the cool thing about this is that I actually kind of read this one pretty recently. So chapter 4 is encoding and evolution. So one, we kind of talk about maintainability, and this is what he talks about a bit here with evolution, which is the idea that like when we make a change to the code, right, it's not going to break stuff in the future. And the other bigger thing is just encoding. Honestly, this chapter doesn't feel like very, very important when it comes to system design, but it's kind of useful, I guess, knowing like how computers are even doing stuff. So with encoding, he's talking about this idea that like when you're coding something in Python or C++, the data object that you use kind of change and modify, right? Like you can have like some service that's doing this, but then you have to send it to another service that's using like Java, right? Maybe we have some application that has like some array, right, in C++, or it has like some, you know, some dictionary in Python, right? But you have to convert that to Java. And this process is called like encoding, right? This is the encoding. And this is going to allow us to send data to multiple places. And so we could even do that. We could even do it for the, what else is it? We can even do it for like another service, like some other like microservice. I don't know. But it's just the idea that like we're like, you know, kind of changing things. And how that works is there's multiple ways of encoding, right? So there's like JSON. This is like the most common, I think, JSON. And there's also multiple pathways of doing it. So there's like HTTP requests of like sending the actual data. There's HTTP. There is like message queues, and then there's like gRPC. These are how we're going to be sending the data to like other services. And then in this method, we can send it using JSON, XML, or like pure binary. right? And this is how like this kind of process is working when you actually have like C++ code and you want to send it to servers, or you have JavaScript, you have a JavaScript web application and you want to send it to the server or something, right? You encode it and change the data type to what it's going to match. Okay, cool. So let's see here. So let me make sure I was right on this, right? Formats for encoding data. So we have in-memory data. We have like data where we want to write to a file or we want to send it over a network. So like sending it to a database too, that's like another thing, right? Like, so instead of just Java, right, we're sending it to like a DB. Send the data to the DB. And then we have encoding and serialization. This is actually a LeetCode problem too, like a little bit, but probably much difficult. And then we can encode it into bytes, right? So kind of what I was talking about is that you can, I guess you have pickle, serializable. And if you do that, I guess you're tied to one language. And you have to decode like bytes, which people can sneak in like malicious code into the bytes that'll just be read like straight up. And then there's no versioning for these libraries. So we get JSON, XML, and binary variants. So we get XML, JSON, CSVs. These are way that people like typically store data. There's a lot of complaints for like each one, but there's not really any other idea. I guess is what Kleppman says in his book. And yeah, specifically, I mean, he brings it like some specific problems, which is like there's ambiguity in around the encoding. I guess you can't distinguish between ints and floating points. You lose accuracy with large numbers. Yeah, but you know, generally just good. It's generally good enough. And then we have binary stuff, so it's going to be fast, which is going to be a good benefit. Send the data fast. BSON, BJSON, BISON, Smile. This stuff, I don't care a lot of too much stuff. So he talks about, you know, how it actually works under the hood. I don't think this is relevant for a system design interview. I don't think that any questions really ask you about this kind of stuff. So I would just skip it. But if you're curious about like how these binary encoding libraries work and like how they can, you know, take a byte and like store it, you know, he talks about like you can create like these structures or whatever. And so we have the data flows like HTTPS, RPC, message queues, right? And database calls. And for HTTP calls, we have REST versus SOAP, remote procedure calls. Not really sure why they use them, but apparently it feels like it's just another way. I don't know. Feels like it's just another thing. I like truly have no idea why you would use RPC over HTTPS. Most of the time, I think it's just HTTP. That's how you send data between things, and then message queues. Cool. gRPC is old RPC. Yeah, the gRPC is greater than, yeah. So it says that like, you know, gRPC supports streams. So you can actually have like streams of data that are being sent, which is pretty nice. And then RPC has built-in support for Avro encoding and stuff. So I guess it's nice for that stuff. We are not even using gRPC a lot, but it just has like, yeah, benefits, I guess. But anyways, that's the encoding section. I don't, you know, it's not really a whole lot, but just kind of interesting seeing how like, okay, how do you actually send data between a database? How do you send it from like your Python to your database, and to your, you know, Python to your server and things like that? It's just kind of all like this stuff. Cool. So that was a fast chapter. Now we're going to the next one, which is a lot thicker. Replication. This is also, unfortunately, I haven't read this one in a long time, but I generally understand replication. So, okay, so yeah, replication. So like, how do you prevent stuff from happening to where you have this system, but you don't want to like lose the data permanently. I believe that's the question that Replication's asking. There's also like, it also helps with scalability. If you have like too high of like a server load, you can, you know, offset it. So one of the first things that Kleppmann will mention in his chapter is this idea of leader follower, right? Which is that you have one leader and then it's going to send that data to the followers. And so if the leader actually fails, it can, the data isn't lost because there's actually copies of it. And leader follower is also nice too, because if somebody's like, if you have like a ton of read requests, they can actually just read from these other servers that you have. From these servers down here, which are the followers. So your only bottleneck is just like your write throughput, which I'm not sure what the number is. I think it might be like, maybe like 20,000 writes per second. I'm not sure how fast a DB can write, but. So let me make sure this is correct, right? Replication is useful for when one system goes down, all the other ones are still going to work. And then the data's not going to change over time. Right, so one, you don't get a single point of failure. And like, I mean, I guess it's useful if your data is not constantly changing. Although I feel like if your data is changing, it's kind of fine. I'm guessing this means like write heavy type stuff, which is what I'm talking about here, maybe. I don't know, actually. So distributed databases must handle the challenge of data changing over time. So we've got like 3 different strategies: single leader, multi-leader, leader-less, which have like just a lot of problems. Leaders and followers, right? I've kind of talked about this. And there's synchronous versus async. You probably want async, would be my guess. And then you can add new followers. But you probably have to just make a snapshot and turn it off if you want to add something new, right? So like if you want to add a new one, your system's already like set up. Well, you're probably either gonna have to stop it briefly and just turn off the system, or I guess you take a snapshot and then just like write over and then have it like follow up whatever the snapshot was. And so this node clones whatever the snapshot was. They get node outages. What are you gonna do if one of these nodes crashes and dies? Right, well now you have to make a new one. And how are you going to make a new one? Right, again, we keep a log of all the changes, and then you restart it. And then just have it read the log. And if the leader fails, well then this is a bigger issue, because now we're no longer getting reads, and we also have to handle like this idea of like swapping. So like if this one crashes, we have to like place this other one here. And again, this is like, this kind of stuff that I'm talking about is like way beyond like a mid-level engineer. This idea of like swapping nodes, I don't think that will ever be asked you in an interview, but you have to replace the node. And then you have to hope that you didn't lose any requests, or that the requests are still like in the log or something. And then the same thing too with split brain, where 2 nodes think they're the leader. Okay, when you go into DB replication or sharding or chunking, async stuff in a system design interview, when do you go into it? Yeah, I mean, that's entirely dependent on the interview. And this is why I say, like, if you're going to do system design stuff or you're prepping for your mid-level, you need to do mock interviews. Because not every interviewer actually cares about testing all of these things, right? Like a system design interview is not, let me sit down for 1 hour and do a presentation. Let me give you a PowerPoint presentation with some diagrams on like how I would build this system, and like how like replication works. Like that's not what it is. It's like you're kind of playing off your interviewer a lot, and you're trying to figure out, oh, hey, what do you want to know? So it'll typically start off with you saying like, oh, hey, like they'll say, hey, do this problem, design like Twitter or whatever. They'll say like design Twitter or whatever, and then you'll say like, okay, well, I would do like this. You're super high level. You just say, I would do this. I would have like this. I would have like this database. And then that's it. And then you wait for them to ask you like questions, basically. So at every kind of phase, you're just kind of like talking a little bit and then letting them ask you questions on what they want to test you on. But you can't just like walk in and say, oh, okay, let's talk about replication, because the interviewer just may not care about that at all. Like, is there a good resource? Other example, gather feedbacks, requirements. Yeah, it's like that's like the strong one, right? And then even then too, right? Like, not all interviews, if it's a 30-minute interview, they will not ask you to do back of envelope typically because you only have 30 minutes. They just don't care about that, and you're gonna kill like they're gonna lose 10 minutes when they want to talk about other things. Feel like that might be why I get not teched up in Path. Yeah, I don't know. It really depends. This is why, again, you should be doing mock interviews, especially for system design. I don't think mock interviews matter that much for DSA, but they do matter for sure. If you've never done a DSA interview before, you need to do mocks, and it's the same thing with system design. And if you don't do mocks, you're gonna fail your interviews, 100%. 100%. It's just like it's very, very difficult to just kind of get this right on the first time. I just don't believe it. That somebody can just never do a mock system design interview and they just walk in and then they can kind of understand like, all of this stuff. So yeah, those are my thoughts on that. That's my thoughts, at least. Would highly recommend mocks. What is DSA? Data structures and algorithms. Where to do mocks? Where to do mocks? Pramp, my interview is almost as lost as me. Well, I mean, the problem with Pramp isn't that you have someone who's going to teach you. The point of Pramp is to do mocks with somebody. Like, it's that you have like someone who's like kind of trying to grade you on some criteria. So like, for example, with like design Twitter or something. I don't know. Didn't Don Martin have his thing here? But no, Pramp is good. Pramp's good. Right? Like the point of mock is just so you can understand and the person can give you feedback on what they think you're doing wrong. Now, I mean, if you really, 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 you say like, oh, well, I don't want to do trade-offs with someone. If you're saying, oh, well, I don't want to trade time and like spend an hour helping another person or they spend an hour like, doing it with me, like, cause I'm kind of wasting an hour or something. Well, then you got to pay money. But that's it. There's a lot of like Discord servers, I think. So like, if you went into, I think, doesn't he mention Discord here? So like, yeah, if you go into like Alex Shu's Discord, Code probably doesn't do system design at all. Honestly, his Discord probably doesn't. But my Discord also doesn't do system design. I'm just kind of starting this stuff, so no system design really for me. But like, if you join like kind of these job boards or whatever, you can maybe have people who are doing mock interviews. I think one thing would be really nice if I can get in my community, like people who actually want to learn and improve, and we get like maybe some kind of mocks with like people who are like better or like probably more motivated than other people. I think that would be nice, like have a community of like motivated people. But anyways, answer your question though, is I think Pramp is fine. Just do Pramp. I mean, if they don't know, then it's fine. Like they're still testing you, they're still evaluating you. So yeah, I think it's fine. Yeah, no problem. Yusuf Elsin Diani. No problem. All right, let's go back into this. So node failures. So yeah, like I said, I think this is out of scope for a mid-level, but just kind of something that you can know is that like, what do you do if a node fails? Probably not gonna get asked it, but what do you do, right? You have to like, okay, kill it. You're gonna have to have some replication log that goes up, and then what do you do if it's like a split brain where this node died temporarily because it failed like the heartbeat checks, and then we swap this one here, but then we actually kind of messed up because this one was still alive. And so now we've got like two things that are like, getting like information. Like that's a problem with this kind of system, is that you have to handle this stuff when you're trying to implement this on your own. It's very annoying. This is why, we have cloud, like AWS cloud, because it already like, it just wipes away all of that stuff. But this is why it's so popular, because this is an annoying thing to have to code for scalability. Okay, implementing replication logs. Write ahead logs, logical logs. Sure. Replication lag. We can just wait. So it's not always going to like catch up immediately. There's always a delay when you're sending data to something. Always some delay, especially when it's over a network. And then sometimes like things just get lost. So sometimes you'll have like messages that are just like gone. Unless you're doing like a message queue maybe, but then you're just going to have delays if you're using a message queue. So now you're introducing delays. So then you just wait. Eventual consistency, just wait. Reading writes. monotonic reads, consistent prefix. I don't know any of this stuff. Probably not gonna bother with that. Multi-leader. You can have multiple leaders, right? So if you have some multiple data centers or you want to reduce latency, this will probably allow you to have multiple. This will allow you to have multiple or a higher throughput, so you can actually record, multiple types of things. Where's the arrow at? Oh, this is it. Yeah, now you can have like multiple, kind of throughputs. Instead of like 20,000 per second, you can actually go to 40,000. And then if you start sharding, that can help too. And then we have leaderless replication. Leaderless is supposed to be like easier when it comes to distributed system because it handles by consensus. Apparently DynamoDB, Cassandra use this, but yeah, this is the idea of replication. There's also like, if you want like an easier kind of thing, right? Obviously there's Don Martin's, where if you go over his replication, it's like master slave and then master master. And where does he have this at? Yeah, like his is just like one page, right? So like notice how I spent like kind of I guess 10 minutes just talking about this stuff. But like his is like, 2 paragraphs, right? This is what I'm talking about. This is what I mean when I say like depth, is that DDIA goes way more in depth. Although you don't need to know this stuff. You didn't, nobody's probably going to test you on the fact that like, what do you do when a node fails, and like, how do you have a replication log? But like, you can just go through and just say like, oh, pros and cons. What are pros and cons? So yeah. And then federation. All right. What else? What else is happening? All right, cool. So with that, let's go into chapter 6. Although I don't know this Don Martin, maybe I should just look at it. Leader follower, additional logic needs to promote a slave to a master, and then disadvantages, replication, but it's the same for both. Right, I think replication is just going to be slow, probably. Data loss, writes are replayed, a lot of writes, read replication get bogged down, requires additional hardware and complexity. Yeah. Disadvantage of master, need a load balancer. But the thing is further reading and stuff, but yeah. Cool. All right, we're going to end this one. This is chapter 5 of DDIA. So we're going to go to chapter 6, partitioning. Cool. Chapter 6. So chapter 6 is related to partitions. And the idea behind partitions is that like you can have a database. You can have like some database, that has like some entries or whatever, but you can query things way faster. Again, we don't have to do O of N. We don't have to go O of N. Oh my God. We don't have to go O of N. Like searching everything. We can actually just group them based off some kind of criteria and like split it. So like maybe A through Z or A through, A to C is here. And then we have another one that's like, D to F or whatever, et cetera, et cetera. And so now whenever we want to search for A, it's actually like a lot faster than O of N because we don't have to search everything. Not everything is like jumbled. So that's the idea behind partitioning, is that you can increase speed, and in some cases, you can have like entire databases that are just dedicated to like the letter A. Nice, I love it. Some databases that are like dedicated to like the letter A or something. Just chill. Cool. So there's also the issue of like hot partitioning. So like this A, B, and C thing it's not practical, because maybe you can have like A's that are taking over, and so it ends up being bigger. It's not like evenly distributed. But I think this is where the hash ring comes in. But okay, sharding, so it allows you to break up data into partitions where each partition is essentially a small database. You can distribute a large data set across many processors, leading to faster lookup times, right? We're not hitting O of N anymore. We're hitting like probably login or even probably login, I guess is what it is, but it's much faster. So we can do key range partitions, just group them, right? You can have some hotspots though, and this is another issue where, again, out of scope for mid-level, I think, or at least maybe for like a low bar mid-level, but you can have like hot keys, and then you need to figure out a way to handle that. So you can have a hash function, right? Just consistent hashing. And then we have here, we can have secondary indices, right? You can also, indexing is like a thing, but you can also have secondary indices, and you can also have like sorting keys and databases. But again, this is like out of scope, but you can have multiple like indices. And then rebalancing partitions. I just did not go through this that much, but I guess look up consistent hashing if you're curious about this. Curious about that kind of stuff. Okay, cool. Now we're back to the stuff that I kind of like studied more recently. I should probably go through the partitions again, but I don't know how much I want to do that. Anyways, we're gonna end this chapter here. I think maybe we can even look at the Don Martin thing too, actually, while we're at it. Partitions. No? Where's my partitions? Partition tables. It's like literally like nothing. Yeah, there's just nothing on partitioning. Anyways, yeah, that's all you would really need to know. So I think so. That's about all you would need to know. I don't think you're going to ask anything more complex than that in a mid-level interview. Cool. So these other chapters are, I believe, like they're higher than mid-level. So you don't really have to like know about this stuff. But if you're kind of curious, I think it's, it's good to know probably. But we'll continue over with chapter 7. So transactions. So this entire one is, I believe it has to deal with like preventing race conditions and preventing like dirty reads, that you essentially have like multiple states of your database. Like what if you have like a database, and what if you have a database and you've got like all these entries or whatever. Oh, you've got like a query, you've got like one query that's going here to here to here to here, and it's like changing stuff. So like now the stuff is like dirty, and then you have like another one that's going like here, here, here. Well, like now your thing is like, now your system is like kind of screwed up. So like how do databases prevent that? And like what are algorithms and strategies that they can use to prevent things? Obviously like a lock is like, a deep one. So you just lock it. So you say nobody can access it, and then they just have to wait. But that's very time consuming. And your system will have like worse performance if you're doing that. So like what ways can we fix this? Right, many things can go wrong, right? We can have hardware that fails, so you were writing something and then it fails, and so it never fixed, and so now you got to like roll back things. I just mentioned you can write to the database at the same time, and in order to be reliable, they have to deal with this. So a transaction is just like a unit of several reads and writes like grouped together. So either succeeds, you commit, or you fail, right? And there is the like all databases support transactions. It's pretty acid. One thing that Kleppmann mentions, is that acid isn't even like defined that well. Like consistent means like absolutely nothing. Consistency means like absolutely nothing. It's not even like actually, there's no metrics for it. It's just kind of like this word people throw out to sell things, basically. It's just like, oh, it's consistent. Oh, this is eventually consistent. But like, what does that even mean? Like, it means that like, yeah, it'll eventually catch up, but like, is there any time limits, right? There's a big range of numbers that you can kind of get through. And yeah, even more vague than acid. So we have base. This is what NoSQL does. So they say like, oh, it's basically available. It's soft state. It's eventually like What does basically available mean? Can you give me like actual numbers on it? Nope. Then we have, let's say, so like what is acid? We go through every single thing. Kleppmann goes through every single thing, which is atomicity. You can have one thread that executes like the operation. There's no half states. We have consistency, and which is generally that like everything's eventually going to kind of catch up to the same data, I believe. And see here, if a transaction starts with a valid database according to those invariants, it's fine. And then isolation. So just no race conditions, no half states, no race conditions. The data eventually like catches up. Right, nothing's going to be like kind of inconsistent. And then durability, right? So that it's going to be persistent, that it's not going to crash or get corrupted or whatever. Like ideally, it's going to like have little, but there is no perfect durability because things can get, power outages can happen, disks wear away. Yeah. Cool statistic. One study found that 30 to 80% of SSDs develop at least one bad block during 4 years of operation. Okay, cool. So there are single object transactions where you have multiple reads and writes on a single row of a database, and then you can have multiple ones where you want to write to multiple rows, essentially, multiple objects, which I guess it's called. And then we have handling errors. A key feature of transactions is that it can be aborted. Weak isolation levels, concurrency bugs are hard to find by testing. Serializable operation. Oh no. Okay, here's like, I guess this one's like kind of interesting, right? So there are different levels to isolation, and it doesn't just go like at the strongest level of like, oh, this will never ever happen, because again, there's the performance trade-offs, right? Like we don't want to just lock this thing and just say, oh, well, yeah, just nobody can use it until I'm finished. There are ones where you can just allow multiple reads, for example, and you can say everybody can just allow to read this one. And this is like the lowest level, and you can set these in a database. So if you have like a MySQL database, you can actually just say like, oh, I'm okay like doing this at like, you know, like the read like level or something, like read, you know, other things can read or whatever. You can have like the read lock or the write onlys or whatever. So serializable isolation. And then, right, it's like preventing performance costs you use, like the weaker isolation level. You can have concurrency bugs. But it's not always needed to have like, oh, let's just be strongly consistent or strongly or whatever. You can have like serializable where you have to do every transaction has to go. But you can have like some, you know, some applications or even a lot of applications where that doesn't matter at all. I guess like one application, if I were to give an example of one, is like maybe like Facebook, like messages, maybe, where you don't really care if a post is like has like some kind of bug in it because nobody's like gonna die really, and especially if it means your page loads faster. But yeah, I think most people would just say like, oh, it needs to be like perfect. You should never have any bugs. Oh yeah, this is it. Read committed. Okay, read committed. That's the first one. Only see the committed data. No dirty reads. And when writing, overwrite data that has been committed. No dirty writes. So like if something is modifying this row and something else reads it, right? You should only read it when this first one finished. You can still read it, but like this one just needs to be like finished and committed. And then dirty writes is the same idea, right? Like if something is writing this, we don't want to allow reading. All of this in which chapter? This is all chapter 7. All of it's chapter 7. It took me 4 hours, 3 to 4 hours just to type the notes on this one, and I'm kind of going through it pretty fast. But this one took me 3 hours, I think. 3 to 4 hours just writing out this, reading it and writing it out. Okay, so there is the implementing read command. So like, how do you even implement something like this? So he goes into how you implement it, which I believe is like versioning, I want to say. Use row level locks. When a transaction wants to modify it, you just lock it. Right, and the problem is that like if one thing locks it for a read, well, we still want to like allow reads, and so what we can do is we can version this, and we can say, oh, if it's locked, just hey, check out the old version. Oh, this is locked. Okay, and then go to the old version of it, and then you return that data, and so now things can go fast. Now things can go faster. Now there is some problems with this, so you could have someone who transfers money to another person. He talks to you as this Alice and Bob example where Alice transfers money to someone. I wish I had the diagram, but I guess I don't have it. I believe it was that like Alice transfers money to someone, so she's like negative like $50, and then that person is like positive $50. But there's like a brief moment where this person looks at what her account balance is, and then it says that she has like and then it says that she has like $50 because like the transaction never finished, which would be like really confusing for that person. And then he calls this like a non-repeatable read or a read skew. Just for a brief second though. Yeah, but this is mostly theory. It doesn't take much time to learn it. Bro, it took me 4 hours to read this book, which, yeah, I mean, it's not a lot of time, but I don't know how many people are reading books for 4 hours. Implementing this stuff, transaction levels, like, this is a lot of stuff to memorize. Transaction, acid, atomicity, consistency, durability. This is a lot. But there's like which is like the reason why most people won't read any of this stuff, and probably most people won't even watch this video that I'm making. But for the people who actually want to learn stuff, I do want to like kind of give this as a kind of like an option. Cap what? I don't know if that was to me or to Bjergsen HS. But yeah, I mean like Bjergsen, this is like this is the hardest kind of concept that if you can learn this thing that is like you're saying like it's very easy, but if you can learn this, bro, you're making $1 million a year easily, for sure. $1 million a year if you can know this information and like put it into practice, of course. But like, because what's going to happen during a system design interview is, yeah, sure, you can draw the boxes, but what they're going to do is they're going to ask you, oh, okay, so like, well, they're going to say, like, one question they could ask is, oh, like, what isolation level do you think we should have? Like, those are like things that they can ask. And why? Like, why should we have this isolation level for this application? Cap theorem. Yeah, cap theorem. Okay, snapshot isolation is the most common solution to this problem. So each transaction reads from a consistent snapshot of the DB. Typically use write locks to prevent dirty writes. Database, multi-version concurrency control. Repeatable read and naming confusion. Calls it repeatable read, something call it this, right? Like, yeah. This idea of repeatable read is different depending on like what database you're using. Preventing lost updates. Atomic rights. Cursor stability. Make an exclusive lock that blocks reads until the update is finished. I think this is fine. This like makes sense. And then replicated databases are like even more annoying because now you have to do this and worry about like different nodes having different types of data. There is another one too with compare and set. Yeah, there's another issue too with compare and set, I think. So like here's like, this is like one issue. And then the other one is that like you can have multiple doctors that need to be like on call or something. And you always need to have one doctor on call. And then if like two of them try to do it at the same time, then it like doesn't work. So you have to you need to compare and set before you do that. So like you can have like, you know, two people who want to like leave, but you need to have at least one, but then you execute the first one and then you execute the second one, but you never checked to see if it was 0 before you did that. And so, you know, this one like should never happen. And so now you've got like doctors that think that they can leave, but they actually shouldn't. So this is the compare and set idea. Okay, and then there's another problem, which is the right skew and phantoms. Oh yeah, so this is what I just talked about, which is right skew and phantoms. If two doctors check out at the same time, a condition can occur. Right, the snapshot will say that both are because there's like just no check essentially that's happening. At least that is what I believe. Characters and right skew. Lost update. More examples. You can have meeting rooms where two people book the same room, but they weren't supposed to. Two people who have the same username in a video game and they try to like claim it. I feel like this is just really difficult. TLDR, this is really difficult. I know this is like, again, I was like, y'all keep saying this. This is above like mid-level stuff, and I'm not going to bother with it, but fixing this seems like it's a difficult problem. Okay, serializability. So we're almost done with this. This is going to be the hardest, the strongest type of isolation level. It's going to also be the slowest. Right, strongest isolation level. It's going to be the slowest. So we just execute transactions in the order that they come in. And then we can also do two-phase locking and maybe some optimistic locking type of control. So like versioning, essentially. And then actual serial execution, right? The simplest way is we just do one action at a time. It's just slow to do it that way though. So when we mean one transaction at a time, right, we've got like all these things that we want to do. So like one, let's say we want to do like, you know, XYZ. And then two, we want to do this one. We just keep the order of them and then just like do this one first and then do the other one and so on and so on. Database can't just sit around waiting for users to make up their minds if they want to book an airline ticket. Transactions are broken up. Application must submit the entire as a stored procedure. Database is much more performance sensitive, no version controls, stored procedures. Partitioning. And then two-phase locking. Which is an algorithm for getting this serializability. And I think it seems like it's defined off this. When someone wants to write to an object, you need the access. If transaction A is being read, then B has to wait for A to finish. If transaction A is writing, then B needs to wait until A finishes. So you're blocking the readers and the writers. So there are several databases that are using this. And it's called two-phase locking because when locks are required, the second phase is when the transaction executes. So the permaface is very slow. And it's very easy to have a queue of transactions that you need to run. And I believe that's it. Serializable snapshot isolation. So then I think this one's just like versioning. But instead of pessimistic locking, we just do versioning. So that's transactions. The TLDR of this, you know, this chapter, again, it was like really long. It took me like 4 hours probably to go through, but we just want to know that ACID is a thing and that there are different levels of isolation, that even with ACID, there's like different levels of ACID. You have this thing called base, which is basically available soft state, right? Just very vague, but there are algorithms and things that we can use and set different types of levels depending on like how disastrous it would be if we had like, you know, an inconsistency in the database or something like, you know, overreading over something essentially. Never seen locking like this common during a system design. Locking? I mean, locking comes in for sure. It comes in, it's a very popular one. If somebody gives you the like if someone asked you to design a booking system, for sure it would happen. So like airline tickets, you know who I kind of like is all this Hello interview people. They've actually done a good job with their social media. They put out some helpful content, but Ticketmaster, like you're probably gonna see that. I haven't read this article, like, and I don't remember it really, but I'm pretty sure they're talking about locking here, just because this is something like you need to be able to lock things. And so, you know, I don't know, the pessimistic locking, right? Like, oh, you just wait. This is like the thing that everyone would think, oh, just lock it and wait. But there's other things you can do. Then again, these people aren't going over every solution, but like you've got ideas. And then, you know, obviously, but like Ticketmaster, there's inventory systems. Not really. What's the other one? Hotel booking systems. Like these reservation applications. They're using this locking type of idea. What is up, Axer? What's up? AKSR 41. You got comfortable with the back of envelope method? Yeah, I believe so. Anyways, so yeah, so that's transactions. That's why we're, you know, kind of go over this stuff. It applies over to some other systems. And I'm gonna end this recording. Cool, there we go. So you got, yeah, like some tricks for back of envelope method too that I use is the 10 to the 6 thing. It's like 10 to the third is like 1,000. 10 to the third is like 1,000. Like back of envelope is really easy because if somebody tells you that we have 100 million users like every day or something, or like 100 million like daily active users, and we need to convert this into like transactions per second, we can do two things. We can, let me actually, can I zoom this in or not? What is up, Hogwarts FKC manager? Thanks for the follow. So like one back of envelope thing is like, so someone's like, oh, well, you have 100 million daily active users and we want to convert this in transactions per second. They're not going to tell you that, but they're just going to say like that. But like you need to convert this into TPS so you can see what's the database load that you need and how many databases you need and like probably how much RAM you need and how much CPUs and all that stuff. Yeah. So one, we have like the days in year, or not days. Was it day 2 second or something? 2 seconds, right? So days to seconds is 10 to the 5th. So anything you do is you're going to divide it by 10 to the 5th. And then we've got 10 to the 3rd is 1,000. 10 to the 6th is 1,000,000, is 1,000,000. And then like 10 to the 9th is like 1 billion. And so on. So what we can do is just take this 10 to the 10th, or 10 to the 10 to the 6th, right? So it's 100 times 10 to the 6th, because we convert an m into a 10 to the 6th. And we've got these two here, so that's actually 10 to the 8th times 10 to the 8th, right? And then what's 10 to the 8th divided by 10 to the 5th? Oh, that's 10 to the 3rd. So that's going to be 10 to the 3rd transactions per second, right? So you can do these things very quickly by kind of just knowing that, as opposed to like pulling out the calculator and running it down. But so now we know this 10 to the 3rd, which is 1000 TPS. So wait, what I did not got that. 100 million. 1 million is 10 to the 6th. Right? 1 million is 10 to the 6th. We have 100, times a million. That means we take these two zeros and we bump them up to here. So that's 1 times 10 to the 8th. And then we divide that to go, this is DAU. So then we convert DAU to TPS, which is 10 to the 8th divided by 10 to the 5th, which is 10 to the 3rd. Right? This is like a really cool trick that you can do. I think just knowing like, okay, M is 6, 9, and you just convert them really fast. Yeah. Daily active users. So again, this isn't true, right? Like I said, like 1 million daily active users, but like, is every user going to do one transaction? Probably not. So there's like some other things that you do. So you say like, oh, well, there's, right, like you can do like, oh, I think every user is going to do this 10 times or something. Like each user does it 10x or 10 times a day or something. Like each user logs in 10 times a day. Well, then you just multiply this by 10. So then you're like, oh, well, then it's 1,000, but they'd be like 1,000 times 10 times a day, right? Or 5 times a day or 3 times a day, depending on the application. But this is how you can do back of envelope pretty fast, or pretty straightforward, I think. Cool. So let's go into this next one, which is trouble with distributed systems. Okay, so for this chapter 8 of DDIA, this one was a pretty short one. Just a lot of it just comes into like how complicated distributed systems are. And really like the core 3 things of it is that you have like you have these 3 things. You have clocks, you've got network connections, and then I think there was something else too. I don't remember though. Maybe it was consensus or something. I don't remember. But like these 3 things make a distributed system so difficult because one, network connections, right? He believes he starts with that. Which are that network connections are non-deterministic, which means they just happen at random times. And it's like, that is so insanely difficult to debug something that just you can't even reproduce. So we got, cloud computing. I don't know sure why he mentioned that, but unreliable networks, right? So requests get lost, they get stuck in a queue, they fail. The server just stops responding, like maybe garbage collection was very long. All these things can happen when you've got multiple servers. That's what we mean when we say distributed system, is that there are multiple servers that are all coordinating with each other to try to get stuff done. And they're all sending data between themselves, like over networks. And EC2 is like crashes like 12 times a month apparently. Most of it just comes from human error. So like a switch is misconfigured. And yeah, glitches. Apparently sharks can bite undersea cables and damage them, and then that causes networks to fail. I didn't know that until I read the book, but this is like, interesting thing. And it seems to be the case that's difficult to tell. Yeah, I've never heard of that. Yeah, apparently, I'm guessing somebody wrote an article. Kleppman mentioned it. Like shark bites network cable. I don't even know. Shark want to bite Google's undersea cables. Wired. Yeah. Shark attacks threaten Google's undersea internet cables. Like, oh my god. I'm like, why? Like, kill me. Why is this happening? Shark's attraction to undersea cables has been well documented over the years. And that is funny, yeah. Yeah, they do it. They love these tasty little snacks. Very delicious, and is responsible for my internet cutting out. But probably like a loss of like $1 million because some shark bit your cable. But yeah, these are difficult to do load, or what's this? I don't know what the many systems automatically detect faulty nodes, like load balancer and things like that. But network is like very difficult because it's very hard to tell like when something fails. Very difficult. Like heartbeats, you know, you can try things, but you never truly know. And there's timeouts, unbounded delays. So you can set a timeout to try to figure out when a network failed. If you never get a response in like a certain amount of time, that means it failed. You have network congestions, data packets. So there's a lot of things that are happening. I think that the network will like automatically like slow it down. Monitors is networking. I don't know what you mean by monitors. I don't think monitors is mentioned here. Virtual machines, sporadic. I think this is okay. Don't think we need to cover that. Synchronous versus async. Why can't we just solve this at the hardware level? Phone uses circuits. Then circuits are synchronous. Yeah, so here I remember he talked about in the book that like why can't we just use a cell phone? Like why is it that like cell phones, like dial up like modems never shut off? Like a fixed telephone networks, why don't they ever shut off? And it's because they're synchronous, I guess. But like our calls can get dropped. Cool. Unreliable clock. So this is the second issue with distributed systems, which is okay. One, we just talked about like how connections are extremely unstable and how they can break and how like they're really hard to track. Well, clocks is another issue where if you have like really sensitive time delays, so let's talk about like maybe high frequency trading, like the stock market where milliseconds matter. You can have clocks that are off by milliseconds. The clocks in a computer use a quartz, which ends up having clock drift. So over time, the clocks get less and less accurate just as they spin. They don't actually like quartz. Quartz as a material does not spin infinitely to the time, like the time of the universe. It doesn't do that. So what happens is they just slowly kind of drift off and get less and less accurate, and they need to be like readjusted. But what this means is that like you have clocks that are wrong, but then also you get multiple servers that all have like their own independent clocks that are all ticking at a different time frequency. So what is at midnight for one clock is, you know, at a different time for another clock. And usually these problems don't manifest until like you actually get to a point where they drift out at a certain distance that's like really, really far, and then you get like this 1 a.m., you know, like the 1 a.m. error where this one says it's midnight and this one says it's like yesterday or something. And fixing this issue is very difficult. It's a problem and it needs to be fixed because you can't just have that happening. So Kleppmann, I think, gives like some ways that you can fix this. So there's monotonic versus time of day clocks. There's two different types of clocks, network time, and then the Gregorian calendar time. And then clock drifts, right? So the quartz clocks, it's about 17 seconds. It needs to be resynced every day. And then you get leap seconds, of course. Again, the universe is a very complex thing. And we get leap seconds. What else is there? The MFD draft regulation for high frequency training only allows 100 milliseconds of clock drift, or requires it, to detect market manipulation in like a flash crash scenario. Yeah, incorrect clocks can go unnoticed. You don't really know until it's broken. and then declare. If it's too hard to, you just have to kill the machine. And then with ordering, he mentions like logical clocks are good, so incrementing a counter. And apparently what we do is confidence intervals for clocks. So we just say like, oh, well, there's a 95% chance it's between this range and this range. And that's like good enough to prevent errors or something. But I believe that was it. Anyways, yeah, I'm skipping this stuff too, but that is his section on basically the problems with distributed systems. And then here we go into consistency, which is another issue, getting everything to kind of be on board with the same data for a distributed system. And this one is actually a really long chapter. Again, this is one also probably took me 3 hours to do, which is how can you just guarantee order? And then we go into like two-phase commit stuff. But honestly, already it is exhausting, man. I've been talking only for like an hour too. Only 1 hour of just going over this stuff. I mean, 2 hours of like streaming, but I took like a 30-minute break to took a 30-minute break. To go eat. Oh wait, is the restream like really, really slow? You can read a OS book or database book, and after that, no one is stopping you. But this feels digestible compared to algorithm problems. Yeah. Yeah, this one, algorithm problems get really complex. They get very complex. I think it's like a 5-second delay or something. Yeah, probably. Q-wordy. What is up, man? What's up? Okay, they charge my computer too. But this is probably really confusing for anyone who doesn't know anything about like systems. Honestly, there's a lot of stuff here. Even like some of these algorithms are actually really hard. All right, so we're on chapter 9 now. We're gonna go through that. After chapter 9, these other ones should be good, but all right, let's run it. Chapter 9, consistency and consensus. This took me like, I think like 3 hours to go through and take all these notes on. And it's tasked with the idea of like, how do you make sure that every node is going to have like its the own data or like the proper data essentially, and like also recognize that they all should have like the proper data. So if one data gets changed here, right, we propagate it down to all the other ones. Cool. So best way for fault finding is finding some general purpose abstractions. I don't know what that. Consensus, getting all nodes to agree on something. Here we go. This is the huge part. How do we get everything to agree? If we have a leader, how do we get everything to agree that this is the leader? How do we start? Which node should be the first leader? Right? And then when the leader switches, how do we know? The idea is things are based on memorization, can be done by ChatGPT. Lagging? What do you mean lagging? You looking back to normal now. Good. Yep. We got this this thing Novatrix. Don't know what it is. Some Colombian healing cream. Gave me my X factor to help my scar. So it's not bad. Still some stuff here, but just keep wearing it, man. I just keep wearing it. I'm not sure if I'm lagging or if stream. Yeah, is anyone else lagging? I worked with Kubernetes And Docker for like 3 years, I know. I'm pretty good. I hope that gives me an edge. For me, it's good. No lag. Yeah. I think it's you Hogwarts. Okay. So yeah. So consensus. So two nodes will usually always have different states. So we generally just want eventual consistency, which means that like if we just wait, like everything's gonna pick back up. And then Klempman prefers convergence. So he calls this thing linearizability, which is strong consistency. This is what like 99% of, I think your interviews for a mid-level are going to be. They're just going to say, we want this strongly consistent, which is nice because I think it comes down to cap theorem. He's probably going to talk about this too, but it's this idea that you can have either, if you want a distributed system with multiple nodes like this, you can either have only consistency, or only availability. And for like the higher level ones, I think they want higher availability, which means like you reduce the consistency, and so you end up getting like eventual consistency where you kind of have to lower down with. But I think for mid level, it's just like we just want like an app that works, I think. And so I think it's generally like just strongly consistent, which is, I think, is kind of nice because then this chapter doesn't really, like half this chapter doesn't even matter because all you need is this. Cool. So big corporation jobs are overrated anyways. I read somewhere on average that a programmer quits Google 1.5 years. Yeah, that's what I heard too, which is really weird. It's a super weird statistic because apparently like the tenure at Google is like 2 years, I think, before somebody leaves. But I know like so many of my friends and even people now, like you look at Simon. Simon's been at Google for how long? Like I think he's been out there for like 2 years, and I bet he's planning on staying. Every like Googler I know has like stayed there for a long time. Why do they quit? Too much stress? No, it's not the stress. Most people a lot of like job hop. It's not stress though. It's definitely not stress. It's like if you look at I don't know, like Glassdoor, Google software engineer, or like Team Blind, Google, like literally everyone's saying like, oh my god, it's amazing work-life balance. The work-life balance, it's like 40 hours a week. Like 4 stars. Oh my god, everybody loves this company. And like work-life balance like 4.4. Like nobody's complaining like, oh my god, the work-life balance is terrible here. I'm so stressed. I mean, like the people are. I shouldn't say nobody, but like generally not. Generally, I think they quit because they want more money. They either want more money or they make a shitload of money at Google. You look at how much money Google pays, like, and they just don't need to keep working. So they put it in their hours and they just like retire or whatever. Like they put in their hours, or I guess I don't know, but I think it's either job hopping. I think it's like having a lot of money and a lot of options, and maybe, yeah, maybe like doing that. Like Nico left pretty fast though. Job hop from Google, they pay well. Yeah, so like here's like the cool thing you can do with here's like a cool thing you can kind of do. I wish this wasn't put up here, but Microsoft, why is this? Why did it close out? I don't want the Colombian companies. All right, hold on. Google, say Google, Meta, or whatever. I don't know. I guess we don't have Meta. Facebook. So let's say you like start here and you're making $200,000. You just graduated from college in the United States and you did your leak code. Now you're making 200K a year. So now you stay there for 2 years, and let's say you get bored, you're tired of that job, or you just want to make more money. You don't, so you job hop. So now you have 2 years experience, so you can actually start applying to like mid-level, and so you just study up your system design, and you can actually pass, and you can like pivot over to Meta. Meta pays a lot right now, but they didn't used to pay this much. But so now you're at like 300K a year, and then you can job hop again. Like there are software engineers who do this. I don't know. Again, I don't know if that many people do it at Google though. But then you wait 2 years, 3 years, whatever. You get bored, and you just job hop again, and now you're ready for like doing like senior level stuff. And so now you can do senior, and now you're making 400K. So like some people do this where they job hop for higher TC. instead of doing like internal promotions, because internal promotion will pay you a little bit less. Honestly, actually, internal promotion pays you a little bit less. I think it's like, I feel like they're probably like 270 for internal, but I don't know. Anyways, this is a strategy that some people try to do. Every 2 years they change jobs. Probably, I mean, they get bored, they're overachievers or whatever. They want to keep doing something different. Market's so bad right now, though. Yeah, I mean, I'm not even sure how many people are quitting jobs right now. I guess we know. Really, most interviews I gave, it was about eventual consistency. Really? Like, if I look at these problems, I don't know about the eventual. Or no, maybe actually, maybe I'm wrong. Maybe eventual consistency is okay, but casual consistency is like another level lower. So there's some where you want like casual consistency or something. I don't know. But this guy's like putting out some good content, man. Look at this content. Look at all this system design stuff. Ex Meta, ex Amazon hiring manager. If he currently works at Amazon, that'd be kind of wild. Ex Meta staff engineer. There's no way he's actually like still working it, right? Yeah, no. Software engineer and coach. Helping people find their dream job. These people, though, I like their content stuff. Their mock interviews are insanely overpriced, though, in my opinion. I mean, maybe it's not overpriced. Maybe this is actually just perfectly priced, actually. I'm wrong. It's just perfectly priced. $160 for 1 hour interview. Or $200, I guess, typically. You get so much money with this stuff. At Google, they work a lot of big systems, very valuable. A level 3, the hop jump skips every 2 years, a solid strategy. Agree. His content is free, very expensive for me. Any tips for passing leak code? Well, you said his content is free. Like the Hello interview, I mean, they post this stuff so that they can get people basically in the pipeline. So this is also free, and it's also not. This is also good advice. This is good advice. It's not like all this stuff I talk about here too, right? Like I mentioned like locking, right? And this guy's like talking about locking. This is when you would use locking and stuff. But like, yeah, this stuff is free. Their website stuff is free. Their coaching is not. They charge 160 an hour, I guess. Maybe probably about 200 an hour. And if it's at a target company, but they'll pair you, I guess, with somebody who works at that company to give you the interview, and so you're getting like I guess a premium on that. And then they have things you can apply to be a coach, make more money, and become a better coach. Yeah. One thing they should be doing is they should be offering training for their coaches for sure. Anyways. Any tips for passing leak code questions if you haven't seen or you remember the algorithm and are struggling to code it live? It's just practice, like TLDR, practice. Practice. The more you practice, the better you get. But companies like Google offer promotion opportunities, so the need to job hop is less comparatively speaking with working at a small. Yeah, I mean, it's less for job hopping. Again, I don't know how that statistic works, honestly. I don't understand the statistic, but I do know internal promotions at Google, you will never make as much as someone who just got an offer. The person who I know who just got his Google offer like last week, he got his offer and it was for about like $310,000 his first year. 310 his first year as a mid-level. But I feel like if I go here and I look for internally promoted people who've been at the company for like 0 to 4 years or something, mid-level or whatever, I feel like, oh, here we go, 0 to 4 at the company. I want them at the company. It's not even going to reach that at all. This is 260. This is what this person got, 260. So there are people who probably who say like, oh well, I want to make 40K more in the year, and so they job hop. I mean, again, these are probably just overachievers though. I don't know how many people at Google do that. I really don't. I really, really don't. Okay, let's go back to this. So linearizability is a strongly consistent idea where also I think I was trying to think of this too, where I was looking at this. Oh wait, no, I'm wrong. Okay, wait, no, I was wrong. Eventual consistency highly available. Yeah, I was wrong with that. So like most of the time you don't want this for your interviews. Most interviewers don't care for strongly consistent. They care about the high availability, and so you get eventual consistency, and that's okay. As opposed to like in senior level interviews where they want consistency and like the availability can like take a hit. Yeah, that was it. That was it. Problems are likely to require stronger levels. This is for the senior, upper bar of senior. And then for staff, it goes like crazy stuff. Yeah, okay. So, but this one, regardless, I still read this chapter, so we can go over it. Um, so after a write occurs, all reads will show the same value after some time. Both seem like can be arranged in sequential order. Serializability is the isolation property of transactions. Linearizability is the guarantee of reads and writes register on individual objects. I don't know what this means. So I don't know what this stuff is really referencing. Single leader replication. How do we ensure there's only one leader? We just have a lock, and we can have a coordination service. I guess these coordination services like Zookeeper etcd do this. And then have consensus algorithms to make sure that everybody knows. So just give it a lock and then compare and set. So how do you implement it? Single leader can maybe do it. Depends on the design. And the problem is you need to know who the leader is. And it's easy for you to have multiple leaders. And then the consensus is always linearizable. Everything it happens by like voting. Multi-leader is impossible due to concurrencies. Leaderless replication. Honestly, I'm probably like too tired. My voice is also hurting, I feel like. I don't think I can actually get through the consistency one, but we get the cap theorem. Clubman mentions here too, that's kind of relevant, but the cap theorem, like this partition tolerance, I believe he says it's kind of useless. Right, like partitions, like we want partitions, we want network partitions, so like that's always going to be a thing. So it's just consistency versus availability. Right, better phrase, but this is just his idea, and I probably agree with it too. I don't know why we talk about partition tolerance like so much, but and then he also says he doesn't like that it doesn't mention anything about network delays, dead nodes, and other trade-offs, but it's been influential, so he like is like whatever. And then ordering guarantees. How do we guarantee the order? And then causality. Oh god, I hate that these chapters are so long. I don't think I can actually go through this. We're at the 2-hour limit, guys. All right, 2 hours of streaming limit. I'm done. Next time I will try to go over these when I have more energy, but I am gassed out for sure. So we're gonna close all these down, and I'm just gonna call it. Well, why do you want to learn algorithms? You already have if you already get jobs easily. Let's say you worked at a company you worked at 5 companies in the past 5 years. Yeah, you're right. Yeah. Twitter, YouTube don't, yeah. If I am competitive programmer, I will job hop every year. I don't care. Nice. Based. But our recruiter's gonna see that you're a job hopper and deny you a job. Let's say you worked at 5 companies the past 5 years. 5 years, a company I don't know. I will get bored, I think. What was this? Men in India. Oh, men in India, they pay nothing. I change jobs every year. Why do you want to learn algorithms? I'm getting jobs based on my tech stack, not on algos. India work culture is not that good. Do you want to work on sick leave? Do you want to go to the US? Nope. Go to Canada? Canada. Canada. The algorithms binge a finality. I like follow this guy a little bit. I don't really know what he does. I never watch his stream, but he's always like doing like stock stuff. Twitch streamers like never have like a YouTube channel. This guy must have been streaming for a long time though to get 10K followers. Probably during pandemic. Why not remote or freelance? One thing to notice if you're gonna do freelancing is that it's a different set of skills. So just be careful of that. But you can make a lot of money either or, but it's different skills. You have to have more sales skills and more advertising skills. Unless you, I guess, pay for someone to do that for you, but then you're cutting into your profits. They're not giving me remote. I applied. Maybe I have to put a lot. Yeah, I don't know. All right, so we're gonna raid Midnight Simon. I'm gonna head out. Anyways, this is like, I guess, a lot of DDIA. You can undercut everyone. Also, you don't want to undercut. That's actually that's a terrible sales strategy. Just undercut. Freelance, I will never do that until I'm at big tech. I'm planning to work on 2 jobs at the same time. Nice. Yeah, no, you don't want to undercut because it's just a race to the bottom. And I think a lot of people, I guess when they're doing like business stuff, they think that like the best way to like get business is that you just undercut. So you just like, oh, well, if this person's selling $100, oh, it looks like my computer's slowing down. If this thing's selling $100, then I'm gonna sell for $50 or something. But then like the quality of clients that you're gonna get is gonna be worse. But then you're just like I said, you're just racing to the bottom. It's like the actual better thing is what you do is you say I'm gonna create something that's. Let me juice the Scalidra. I don't know if this is gonna help my speed, but the like the better thing is you say I'm gonna offer something that's worth. I'm gonna convince somebody that I can make them like $1 million or something. Like that's gonna be way better. Yeah, my computer is we're really at the limit. It's just gassing out. So stream done. But the better way is you just come up with an offer that's gonna be worth like $1 million instead of like trying to like fight down for like $50 like tickets or whatever. And I can't even draw on it, so whatever, fuck it. But whatever. In India, he needs way less money than someone in the U.S. Well, yeah, I know. I live in Colombia right now. I know that. Okay, what I'm saying is if you're gonna start a business, if you're gonna start any business, if you're gonna do freelancing, if you're gonna like start some app on the App Store, the best way like for you to make money is like if instead of charging like $1 for your App Store app, make an app that's worth more than $1 and then it'll work, right? Like, um, because a lot of people think that like, oh, well, if I just make like a shitty product and I charge $1 for it, or if I do like a semi like good thing and I just charge like $20 for it, well, it's so cheap, you should just buy it. But you know what gets people to buy it is if you have a product that's so good, so amazing, and then you can charge like off of that. So you can charge like $100 off of that or something. It's up to you, I guess, for whatever business you want to do. But like you get two options where you can just make a really good product or you make a mediocre one and give a mediocre offer to the person. I'm talking about remote job or freelance, not business. Oh, well, yeah, like remote job. I don't know if you can really negotiate for working for pennies. I guess I don't think that's a thing for software. But for freelancing, if you're talking to like other people, like I mean, you're effectively running a business. Where freelancing is a little bit different because you're talking to an actual business owner. You're talking to like one individual owner. For companies though, like I don't know if startups just say like, oh, well, let's just hire someone for $20 an hour. I don't know. I don't know anyone that do that. Like like if you're just getting started doing freelancing, I guess I could see like doing it for free, but it doesn't make a whole lot of sense to me to do like again like those like $20 Upwork jobs. What is up? Beer. I can't even see it actually. Beer on it. Beer Yan Eep. I don't know how to pronounce that, but what is up? Thanks for the follow. If I have money, maybe not. But I don't know. But after that, I have problems with the government policy. 1.5 billion people there. Your government doesn't care about you. They only care who can vote. India is more of a socialist country. I don't know anything about India, so I can't comment on any of that. Can't comment on any of that. But anyways, yeah, for like a lot of stuff too, like business freelancing, like that kind of stuff where you're talking to individual people or like, customers or I guess maybe small businesses that have control over that kind of stuff. I think you can come to kind of deals. I think it's kind of like a balancing act though. It's kind of weird because I think that one, there's companies that will say like, oh, well, you would never work for $20 an hour or you would never work for $5 an hour. And so like, we're just not even going to bother hiring you. Or like you could, destroy our system if we don't think you're a good enough candidate. But I think that also like I think they don't do that because they think you'll just quit once you get a better offer that's actually like at the market rate or something. Like if the market is like $100 an hour, I think that they'll say like, oh well, if we pay you $5 an hour, like even if we finesse and we can kind of like convince you, I don't know. I think that's like the reasoning behind it. I have no idea though. Anyways, I'm gonna head out. So a lot of India. Indian government is rich, top 4 in the world. But they understand that in India, you need way less. These companies aren't stupid. So you've been saying get a remote job in the US? I thought you're saying get an India job. Get a remote US job that pays you 20 an hour. I mean, that probably works. That probably works. You can get a remote job in the US that wants to hire someone in India for cheap. That probably works. Or you freelance, I guess, for that thing being cheap. Sure. I don't know. I think the problem with that is for US companies hiring people like that, I think it maybe there's like some, I don't know, legal issues. I'm not sure how that works. Like when you hire someone in India for cheap, that does not mean you get quality. Quality people in India do not work in jobs. Yeah, they run startups. Yeah, yeah. Yes, freelance, not legal employment. Yeah, but like the it's a dicey thing. I don't know how that would work, but yeah. I've been saying too for a bit too, but like I think that if you can speak English, you can really get a big leg up by because you can service like the United States, the US market. You can service the US market for sure. Also, I think my ad is running. I was waiting for my advertisement, I think, to go off. But yeah, no, I mean, I think that probably works. You could, I don't know how, I really don't know how it works for software though. But like you could definitely find like some freelance project to work on for like $20 an hour, I think, in the United States. But the problem is, how do you find those? Like, I don't think you're gonna find those from job postings, right? We're talking about freelance, and then for startup jobs, I don't think startups are really looking for $20 an hour people in India. Like, not like the ones on Hacker News or something, Hacker News jobs. But you could find someone. I think you could probably find like some small business owner who doesn't know a whole lot and is like looking for someone. But like these companies, they're not hiring Indians. Like that's not like their go-to is like, oh, let me hire someone from India, who's not in our time zone. Like they literally, yeah, they're kind of big on that. Anyways, anyways. I'm gonna head out. Peace, guys. Good luck. And I hit my 2 hour limit. So we're gonna be heading out. All right, yeah, good luck on the interview prep, guys. Good luck on studying, and I'll see you. Bye. Chandu Bjergsen HS. Peace. See ya.